So let's talk about gravitational fields a little bit here. Won't take too long. Okay, so we know that around a mass, we've sort of looked at this a little bit. Around a mass. Okay, so um, gravity is a force that acts between masses. Okay, so if this represents the Earth, around the Earth there is a gravitational field. We're going to represent that field as a bunch of arrows pointing towards the center of the Earth. Okay, so no matter where you stood on the Earth, you would be pulled towards the center of it, right? Now, the strength of this field changes depending on your distance away from the Earth. And if you were like next to, a smaller planet or a larger planet or whatever, depending on the density and the radius or the mass and the radius of this planet's circumference, or not circumference, what's the word I want? The radius of the planet, okay, would change the gravitational field strength around the planet. So in order to test the gravitational field strength, we would need to bring a test mass into the field and basically test how this field affects the mass. Okay? Near the surface of Earth, the field strength is 9.8 newtons for every kilogram. Okay, so this number may ring a bell. This is the field strength near the surface of Earth. Every kilogram of mass you put will feel 9.8 newtons worth of force from the gravitational field. So if you put 2 kilograms, you get 2 times that. Put 10 kilograms, you get 10 times that, and so on. All right? Now I just want to look at this. So this is the number of newtons of force you get for every kilogram that you put in the field only near the surface of Earth. As you go farther out, this number decreases, okay, but near the surface you get this. What units make up a newton? Do you remember? Well, force equals MA, right? Mass is kilograms, yeah, meters per second squared. So what you have here is you have kilogram, meters per second squared times kilograms to the power -1, or per kilogram. So kilograms come off of there, they cross out, they cancel out, and you get meters per second squared as another unit of gravitational field strength. So what is that? Well, that is an acceleration, and that is actually the acceleration due to gravity near the surface of Earth, and we call that g. Okay? So the acceleration due to gravity near the surface of Earth, we call that g, and it's 9.8 meters per second squared. It's also nice to think about it in terms of its kind of alter ego, the gravitational field strength, in that every kilogram experiences 9.8 newtons worth of force at the surface of Earth. Okay, let's use g here to solve a problem. Okay, now one little note. We're going to talk about objects that are like falling towards Earth, okay, or objects that we're throwing up in the air. And then we're going to talk a little bit about weight, okay? We're going to neglect air resistance because it makes the math a lot more difficult if we put air resistance in there, okay? And it adds an extra variable that just makes it difficult. So we're just going to pretend air resistance isn't there. In real life, you can't obviously do that, but just for the sake of our learning, let's neglect it. So here's an example. A person throws a ball up at 15 meters per second. Calculate the time it takes to slow to 0 meters per second. Then find the height it reaches. Okay? So you're going to have to use some kinematics for this. I like to draw a picture to start all my problems. So let's say there's a ball. It starts with an initial velocity of 15 meters per second. Okay, it's going to rise up. There's going to be a downward acceleration due to gravity on it of 9.8 meters per second squared. We need to know the time it takes to get to its max height. So looking at some of the formulas that we have, we need one that deals with acceleration. So we know this. A equals delta V over delta T. In this case, A is special. It's the acceleration due to gravity. And we want to solve for time. So rearranging the formula, we get this, delta V. And I'm just going to exchange the A for G. All right, so what's our change? So we have final minus initial. So our final velocity is 0 minus 15 meters per second. That was the initial velocity, divided by negative 9.8 meters per second squared. Okay. It's important that you keep your signs straight when you're doing these problems. If you're ending up with a value of negative for time, something isn't right. So then you get, if you solve this, you get 1.53 seconds. Okay, so it takes 1.53 seconds for that ball to stop rising and reach its final velocity of 0 meters per second. At that point, it can't go any higher, and it starts to accelerate back down towards the Earth. Okay. Now we want to, figure out how high that went. So if we want to do that, we need to use our formula that deals with accelerating objects. So Vf plus Vi over 2 times t. So in this case, our final velocity is 0. Our initial velocity was 15 meters per second, divided by 2 times the time that we solved for before, 1.53 seconds. You get about 11.48 meters. And there's a typical problem type that you might get dealing just using G. Okay.